Up to this point, we've done a lot of differentiating, but we know in math that if we can do something one way, we should be able to undo it. And so we're going to undo derivatives, and we're just going to call it for now the antiderivative. So if we have a derivative function, so for example, we're going to let the big F be a function, and the derivative is going to be this little f, which means that the derivative of the big F is equal to the f of x here. So this f of x, which is the derivative, is x squared. I want to know what function differentiated gives us x squared. Well, this isn't all that hard to do because we know that based on the power rule, if I differentiate some cubic function, I end up with a quadratic. Okay, so I know that the big F must be some cubic function. The problem is, if I differentiate this, I'm going to end up with 3x squared. Well, I don't have a 3 in the front here. So this needs to be accounted for that as I apply the power rule, I'm going to end up with a coefficient I don't want. Well, I can easily account for that by just dividing by 3. So now differentiating this, I'm going to end up with 3 divided by 3, which is 1, and reduce the power by 1 is x squared. Yeah, that's the right function. But we also have to account for the fact that, well, if this was differentiated, there could have been some constant value here that does not show up in the derivative. So that this, if I differentiated big F, this plus c disappears in the derivative. So I have to account for the fact that there could have been a constant. So basically what I've done is I've used the reverse of the power rule and I've just accounted for the fact that there's a plus, there could have been a plus c there. So I'll do the same thing for this one. If I ended up with a cubic function as a derivative, my original function must have been a 4th degree polynomial. Because I differentiate power 4, I get power 3. However, the coefficient, if I differentiate this, I'm going to end up with 4x cubed. I don't want that extra 4, so I account for that extra 4 by just dividing by 4. And again, there could have been some constant that was in the big F function when differentiated doesn't show up in the derivative. For x5, I needed to start with an x to the power 6 to make the coefficients match. I need to divide by 6, and I always have to remember to account for the possibility that there was a constant that disappeared when we differentiated. And so we're going to call this big F value the antiderivative function. And basically what we know derivatives is, well, in math, if we can go one way, differentiate, we can go the other way and anti-differentiate. We're also going to call this process integration. We're going to integrate going from the derivative back to the original function. And what we also know is that that integration has something to do with area under the curve based on our last examples. But we're just going to kind of have that in the background. We're not going to look too closely at that, but we know that they must be related. So the integral notation looks like this. The antiderivative, or the integral, okay, so when I talk about the integral, I'm also talking about the antiderivative. If I want to find the antiderivative of this x to the power n, I can undo the power rule by increasing the power by 1 and dividing by that power because we want to make sure that the coefficients match. We also have to account for a plus c. So this is anti-differentiation, or what we call integration. It can also be written as a differential equation. So we can say that the derivative dy by dx is equal to x to the power n. This means that x to the power n is the derivative, and what's implied is we want to solve for the original function y. To do that, we again anti-differentiate by using this same rule. Okay, so this is in its integral form, this is in a differential equation form. They are essentially the same thing. We are both cases being asked to find the antiderivative.